Hey everyone, Mr. Hauk here. In today's video, we're going to be looking at complex number operations geometrically. So previously, we looked at how we can add, subtract, and multiply complex numbers algebraically. Now we're going to look at doing those operations on a graph. We're going to begin with adding complex numbers graphically. So the problem that we're going to concern ourselves with is this problem right here. We want to add the complex number 1 plus 4i to the complex number 7 plus 5i. And I'm going to go ahead and take us through the steps on how we can do that graphically. So the first step is we want to represent each complex number as a vector on the complex plane. So let's go ahead and do that. I'm going to represent 1 plus 4i as a blue vector. So coming over here, here's the vector 1 plus 4i. And I want to represent the complex number 7 plus 5i with a green vector. Again, these are just the colors I'm choosing. But here's that vector 7 plus 5i right there in green. So once we have these two vectors graphed, now we're going to use the parallelogram rule for vector addition. Remember, the parallelogram rule basically said if we have two vectors that share the same common endpoint, notice these two would share the same endpoint there at the origin, then we can create a parallelogram using those same two sides. And it turns out that the diagonal of that parallelogram represents the sum of these two complex numbers. So notice we went through when we completed the parallelogram, and here in red I have the diagonal of that parallelogram. And if we go through and count, we would have 8 on the real axis right here, and then 9i on the imaginary axis right here. So the sum is 8 plus 9i. And again, this is how we can find that sum graphically. Now, we can always back that up algebraically. We can say, okay, if I want to add these complex numbers together, let's add the real parts. 1 plus 7 would give us 8. Let's add the imaginary parts. 4i plus 5i gets us 9i. And we can see that everything checks out. Okay. Here in our notes, we also have a second example. We want to, on the same complex plane, represent the sum graphically of negative 6 minus 2i. I decided to do that here in dark blue. And then plus the complex number 1 minus 5i, I did that in dark green. And we can see again, using the parallelogram rule, completing the parallelogram, looking at the diagonal from the origin along the diagonal there, we get a complex number negative 5 minus 7i. And once again, we can verify that algebraically. Negative 6 plus 1 is negative 5. Negative 2i plus negative 5i is negative 7i. So again, adding complex numbers geometrically, we would use the parallelogram rule for vectors. Now let's take a look at what we would do to subtract complex numbers graphically. And essentially, it's going to be the exact same process as adding, but we're going to be adding the additive inverse. So here's the example we want to consider. We want to do the complex number, let me go back, negative 2 plus 3i minus the complex number 3 plus 6i. So here's the strategy here. Again, we want to represent each complex number as a vector in the complex plane. So in dark green, I did 3 plus 6i. In dark blue, I used negative 2 plus 3i. And here they are graphed. So here's 3 plus 6i. Here's negative 2 plus 3i. Notice I'm not doing anything yet with the minus sign in the middle. So I'm just graphing the original two complex numbers as vectors. And then what we want to do is we want to graph the additive inverse of the complex number being subtracted. So 3 plus 6i is being subtracted. The additive inverse of 3 plus 6i is negative 3 minus 6i, which I did right here in this little dashed green. So here's the additive inverse of 3 plus 6i, negative 3 minus 6i. And then what we want to do is we would just want to simply use the parallelogram rule with the first complex number and this additive inverse of the complex number that's being subtracted. Using the parallelogram rule, we get this complex number, negative 5 minus 3i. Okay. Here's another try one example. You can go ahead and pause and try it and unpause and see if you got it right, or you can just follow along with us. But the second example, we want to try to take negative 4 minus 5i, which I represented here in dark blue, minus the complex number 1 minus 6i, I represented here in dark green, Again, it's a subtraction problem, so we want to take the additive inverse of 1 minus 6i, which is negative 1 plus 6i, and using negative 4 minus 5i right here, and the additive inverse of the vector being subtracted, then we do the parallelogram rule, and we get negative 5 plus I on the diagonal there. And we also show algebraically that this result is correct. We see algebraically negative 4 minus 5i minus 1 minus 6i. The negative ends up getting distributed. So we have negative 4 minus 5i, then minus 1 plus 6i. And we can see negative 4, negative 1 combines to negative 5. Negative 5i and positive 6i gives us a positive I. So we can see algebraically and geometrically we got the same result. Okay. Now let's take a look at multiplying complex numbers. Let's begin by graphing the complex number z equals 2 plus 3i. So again, we're just calling this complex number z, real part 2, complex or imaginary part of 3i. And right here in dark blue, that's z. So I'm just going to go ahead and put a little z right there. So on the same plane, we're going to graph 2 times that complex number z. So 2 times the complex number 2 plus 3i. If I distributed the 2, I get 4 plus 6i. And notice I did that one here in green. So this is 2z right here in green. Don't let the colors fool you. This vector is starting at the origin. So all the way from the origin to that point in the complex plane to 4 plus 6i. Let's also graph 3 times the complex number z. So that'd be 3 times 2 plus 3i. Distribute the 3, that gives us 6 plus 9i. So that's all the way out here. Okay, so that's 3 times that complex number z. And then let's also graph the complex number negative 2 times z. So negative 2 times 2 plus 3i. Again, let's distribute the negative 2. We get negative 4 minus 6i. So negative 4 on the real part, negative 6 the imaginary part, and that's down here. So one of the interesting things to notice is that each one of these real multiples of this complex number z results in a vector that falls on the exact same line. And if we were to put this in the xy coordinate plane, this line would be y equals 3 halves x. So notice, again, all these real multiples of this complex number all fall together on the same line. In this case, y equals 3 halves x. Very interesting. So that's when we take a real number multiplied to a vector. It essentially just extends that complex number as a vector across a single line. Let's look at some powers of I now. So this is a pretty cool and interesting result. So first, we know that, because of the way that we defined our real axis and our imaginary axis, let's say that I is right here, positive I. Well, if I wanted to graph I squared, well, I know I times I equals I squared, and we know by definition I squared is negative 1. So we have over here negative 1 equals I squared. Okay, well, what about I to the third? Well, I to the third is I squared times I, and we know I squared is negative 1, so negative 1 times I. So I to the third just so happens to be negative I. Okay, well, what about I to the fourth? Well, we know I to the fourth is I squared times I squared, which is negative 1 times negative 1, which is positive 1. So I to the fourth just so happens to be positive 1. And notice that every time we are multiplying by I, we just end up getting a 90-degree rotation of the point counterclockwise. If I went from I to the second power, this point just rotated 90 degrees. Going from I to the second power to I to the third power, this point here rotated 90 degrees. Same thing here, I to the third to I to the fourth. This point here rotated 90 degrees, all counterclockwise. And we can see the same thing here with I to the fifth through I to the eighth. if I to the fourth was right here, I to the fifth, rotating 90 degrees, would rotate back here with I to the first. Then we'd have I to the sixth, I to the seventh, I to the eighth, and that pattern would just continue to cycle over and over and over. So where do we think I to the 11th would be plotted? Well, we can count, right? If this was I to the 8th, we know I to the 9th would be here. We know I to the 10th would be here, which means I to the 11th would be here, with I to the 7th and I to the 3rd and negative I. Another way we can look at this is we can just subtract 4 as an exponent, right? 11 to 7, that's minus 4. 7 to 3, that's minus 4. So on and so forth. So that's another way that we could have approached it. It's a very interesting result. Multiplying by I results in a 90-degree counterclockwise rotation. And that doesn't just apply to, multiplying just I times I. We're going to see here that it also applies to multiplying any complex number times I. And here's the proof here. So let's say that the complex number z is 3 plus I. And I graphed that over here in blue. So here's 3 plus I. Well, let's go ahead and multiply 3 plus I times I. So basically taking the complex number z times I. Well, that's going to give us, after distributing the I, we get 3i plus I squared. But again, remember that I squared is negative 1. So we get negative 1 from the I squared plus 3i. So I'm going to graph that here in green. Negative 1 plus 3i right there. And notice once again, we're just getting this 90-degree rotation counterclockwise. Well, let's keep trying it here. Z times I squared. So instead of just doing z times I, now we're doing z times I squared. So that's I squared times 3 plus I. We'll distribute the I squared. We get 3i squared plus I to the third. From above, we already know that I to the third is the same as negative I. So we get a negative I here, and then 3i squared. We know I squared is negative 1. 3 times negative 1 gives us the negative 3 here. So we get negative 3 minus I, which I plotted right here in red. Once again, notice the 90 degrees counterclockwise. And the cycle just continues. If I did z times I to the third, okay, well, I to the third times that original complex number z, we get 3i to the third plus I to the fourth. We saw previously that I to the fourth was positive 1. And we know that I to the third is the same as negative I, so 3 times negative I gives us negative 3i, and that plots the point 1, negative 3i. Once again, showing another 90 degrees counterclockwise rotation. So the big takeaway from this, what do you notice each time you multiply by I? Well, each multiplication by I, again, rotates the point 90 degrees counterclockwise, or I'm just going to write CCW, around the origin. So lastly, we talked about multiplying complex numbers by a real number. We talked about multiplying a complex number times I. Now let's just talk about a little more complicated versions of multiplying complex numbers. Let's multiply a complex number times another complex number. So in this case, let's let z be the complex number 4 plus I, and let's let w be the complex number 1 plus 2i. I'm going to go ahead and graph z here in blue, dark blue, so that's right here, 4 plus I. And then w is the complex number 1 plus 2i. I graphed that here in green. And we want to graph the product z times w. Well, first let's go ahead and figure that out algebraically. So z times w, 4 plus I times 1 plus 2i. Well, let's use the FOIL method. So 4 times 1, we get 4. 4 times 2i, we get 8i. I times 1, we get I times 2i, we get 2i squared. Simplifying, we know 2i squared is just negative 2. 4 and negative 2 creates a positive 2 for the real part. 8i and 1i gives us 9i. So z times w, the product of those two imaginary or complex numbers, gives us the complex number 2 plus 9i, which I decided to graph here in black. Now, we want to figure out, is there a relationship here? And it turns out there is a pretty nice relationship. And to see that relationship, let's look at the modulus of each of these complex numbers. So if I calculated the modulus of z, remember modulus being the length between the complex number and the origin, So if I calculate the modulus of z, well, that's going to be the real part squared plus the imaginary part squared. Add it together, take the square root. So the modulus of z turns out to be the square root of 17. The modulus of w, so doing the same thing here, real part squared plus imaginary part squared. Add it together, take the square root. We get the modulus of w is the square root of 5. And then lastly, let's go ahead and take the modulus of the product, z times w. Well, again, we know z times w is 2 plus 9i. Calculating the modulus, that's going to be the square root of 2 squared plus 9 squared. That gives us the square root of 85. So is there any relationship between square root of 17, square root of 5, and square root of 85? Well, notice the square root of 17 times the square root of 5 would give us the square root of 85. So based off of this example, example is not proof, but it's looking like if I multiply the modulus of one complex number times the modulus of another complex number, it's going to give us the modulus of the product. And in fact, that is actually what turns out to be true. So the modulus of the product of two complex numbers is simply equal to the product of the modulus of each of those complex numbers. But we can also say something about the argument, and it's a little harder to see here. We'll give proof later. But remember, the argument is the angle that the modulus makes with the real axis. So it's hard to see here, but if I added the angle created here with z to the angle created here with w, these two angles added together would actually give us the angle from the product z times w. In other words, the argument of the product is the sum of the individual arguments. Okay? So we have one extra little practice problem. Let's go ahead and try it out here. We want to graph the product negative 3 plus I times 1 plus 2i. I went ahead and graphed negative 3 plus I in dark blue. I graphed 1 plus 2i in dark green. And we can see, just kind of looking at the graph here, we have this angle here, this modulus, or not this modulus, the argument from 1 plus 2i. We have the angle here, the argument for negative 3 plus I, and it's looking like this angle plus this angle is certainly going to give us that full angle for the product of those two complex numbers. And the product of those two complex numbers turns out to be negative 5 minus I, which is what I have graphed here in black.